I'm here to tell you about what we're doing with quantum computing at NVIDIA, and hopefully leave some time for you to ask any questions, but to tell you how we're working with almost everyone else in quantum computing to try and make sure that we get to commercially and scientifically useful quantum coprocessors and supercomputers as soon as possible. And to kind of kick that off, I wanted to start off by giving you the introduction I always give, which is to explain why at NVIDIA we care about quantum computing. It may seem kind of obvious, we're a big computing company and every big computing company is interested in this one way or another, but for us it really feels more like it's part of our DNA. So we have a history about finding ways that compute can be used to approach and tackle new problems, things that people didn't necessarily think compute could be used for in the past. And so there's a list of kind of key moments here in where we've helped GPUs make that change, whether it's in deep learning or generative AI most recently. And as far as we're concerned, quantum hardware is the next step in that journey. And although at NVIDIA we're not trying to build quantum hardware, we're not building qubits, we are trying to build devices that will take those qubits and turn them into useful quantum computing devices. And we call that kind of a machine an accelerated quantum supercomputer. And by that I mean a device that combines both quantum and classical hardware resources to allow us to run the kind of large-scale, commercially and scientifically useful applications that we all have sort of dreamed of for quantum computing. And the reason that we have this name for this particular device is because it's really important to realize it is more than just a quantum processor. And in a device like this, you have conventional AI supercomputing integrated with quantum hardware. And so throughout this talk, whether I like to or not, I will use the term accelerated quantum supercomputing because I say it so much in my life. This is what I'm talking about. I'm talking about a hybrid quantum classical device. So why do you need that? I mean, look, okay, obviously I'm for NVIDIA. You think I'm going to say that you need classical supercomputing for quantum computing, but what is the evidence? What's the argument behind that? And there's at least two really good ones. The first is that any kind of application that you want to run that you would think of as a quantum application is at heart a hybrid application. So that might be very familiar from NISQ. When we think about NISQ and the things people have proposed so far for like earlier quantum systems, they're normally inherently like calling a QPU within something like a machine learning loop. So there's clearly a really tight sharing of computation between classical and quantum subroutines. But even larger kind of fault-tolerant algorithms fundamentally are not just purely quantum, even though we like to think of those as quantum algorithms, things like phase estimation. Those ultimately also need pre-processing and other classical subroutines in order for them to work, inevitably. And that's just one thing. So if you're thinking of running an application, you really want a system, a platform, an architecture where a developer can easily and fluently distribute tasks, perhaps even under the hood without having to think about it, to these different shared hybrid modalities of compute. But another thing, which I've got down the bottom here, is that to actually keep quantum hardware ticking along at all, to make a QPU run in the ways that we think we need it to for many of the useful applications people dream of and think of and are developing today, we need to do things like quantum error correction. We need to do things like control and calibration, and those are extremely computationally demanding tasks. Not only do they need very intense computation to do things like run the classical decoding algorithms that I'll talk a little bit more about in a second for quantum error correction, they also need those computations to be handed off with extremely low latency, and they have extremely high throughput in the amount of information you need to process and receive and send from quantum hardware in order to do that. And so this is a vision that we have for how useful quantum computers will look. We today have a software platform and, of course, the hardware piece of this puzzle on the classical side that we're bringing to the community so they can start to research this kind of system, understand how it will work, and develop applications for it in a way that are actually going to be such that they can develop applications that will persist in this kind of future model for how quantum computing will join supercomputing. Okay, wow, this really looks hard to read on this slide. So the exciting thing is, I've been interested in quantum computing since I was 14. I am absolutely a huge nerd, and I love it, and I will never not be thinking about quantum computing. But this, I think, is one of the most exciting developments in quantum computing since I've been interested in it. which is that today people are talking about building and are building logical qubits. So I'm sure nearly everyone here will understand what I say when I say that, but just in case, real qubits, physical qubits, if you think of like a superconducting qubit or a trapped ion itself, they are inherently noisy. They experience errors. Somewhat miraculously, it was discovered in the 90s that there's a way around this. There are things called quantum error correction algorithms. It was never obvious these things could work, but they do, and it's amazing. But to get them to work and effectively distill from noisy qubits perfect logical qubits, you need a lot of overhead and you need a lot of control systems, and it is not a simple task. And so people demonstrating logical rather than physical qubits is a huge achievement and a real step in the right direction for large error-corrected fault-tolerant systems that we believe we need for many of the kind of textbook proven to be incredibly powerful quantum algorithms that we talk about. And so this is just to show you that in the white bullet points you can see already people are starting to demonstrate kind of prototypical systems that kind of show how you would do what you need to do to build logical qubits, but also, and these are data points that are very roughly and coarsely averaged over many different roadmaps from different companies and organised by modality. Also, there are predictions for this scaling in a way that we really need it to, really importantly. This slide will definitely get me into lots of arguments, and there's a lot of error bars and everything on this, including the y-axis. Like, I've kind of put estimates here for how many logical qubits you need to do different things. This can be debated a lot, and I hope it's a lot easier than that. I hope that we find ways to make algorithms need even fewer logical qubits to be useful in various different definitions of useful. But it gives you an idea of where the industry is going. And most importantly, it shows you why these are three of the biggest challenges that I think the industry faces in going from where we are today, which is incredibly impressive demonstrations of physical and now logical qubits, to large-scale accelerated quantum supercomputers that perform error correction and can run the kinds of scales of applications that we all, I think, really care about. Those three challenges are: we need better quantum processors with lower noise to begin with before we even try and error correct them. We need better algorithms that do a better job of using the resources that we will have available, and also perhaps expand the application areas we can use quantum computing in. And we also need to make the quantum error correction approaches we have better and scale more, so as we build bigger systems, it's tractable to actually implement them. And I'll talk very shortly about that, but I just wanted to show you that actually, like, around the world, people are on board with this idea of bringing quantum hardware into supercomputing centres in order to start to solve those problems like quantum error correction and run hybrid algorithms. I put up a list of some of our fantastic partners around the world who are not only amazing supercomputing centres that are often using our hardware, they're also centres that are working with QPU builders to integrate, to begin to experiment with how you do that integration of quantum processors into their systems. And so this is a testament to the idea that this vision of accelerated quantum supercomputing is the right way to go. And the other thing I wanted to say, which I've not dwelled on yet, is that as well as supercomputing being an important part, accelerated conventional supercomputing being an important part of the final way we think a quantum computer will look, it's also the tool that is helping us get to that point. So much of the research we're doing today to improve quantum hardware and quantum algorithms is being enabled by supercomputing systems. And so GPU accelerated simulations, both of hardware and software and their algorithms, is really key. And there are many systems that are planned that are going to use the next generation in our GPU technology and really be centres at which quantum research is going to nucleate around. Okay, so the platform that we have now that is enabling this, we have a software platform. There's several different kinds of software in there, and all of these are designed to allow researchers, many different kinds of researchers, to use the latest in AI supercomputing, in accelerated supercomputing, GPUs and CPUs, to do the quantum research they need. And I'm just going to call out some of these pieces of software very quickly, so you know what I'm talking about. QWC is our platform, which is an environment in which developers can write hybrid algorithms. So they can write algorithms, and a lot of what's done in QWC, the kind of kernel-based programming system it has, like takes away or obfuscates the kind of difficulties in addressing both classical and quantum hardware from one piece of code and makes that easy. So it's the platform for developing these kinds of algorithms for hybrid systems, and we partner all across the software and hardware ecosystem to make that possible. So under the hood, QWC can connect directly to actual quantum hardware. And so our QPU ecosystem partners are providing their QPUs, well, you can access their QPUs through QWC. And we also have a huge software ecosystem that plugs into and is compatible with and integrates with QWC, because the whole goal of this is just to enable as many researchers as possible, however they're doing their work, to have access to the tools that they need to advance quantum computing. Now, in this list, I've kind of put things in an order from top to bottom, so I didn't talk about it, but QWX, I will say something about it shortly, is some higher level libraries that draw on QWC and give kind of packaged functionality in areas like quantum error correction that researchers need, so they don't have to rewrite code, and there's a lot of useful stuff in there. QWC I just described. Under the hood, QWC, as well as controlling actual QPUs, can run GPU-accelerated simulations of QPUs. So if you don't have access to a QPU, or it's too expensive to test something out on one, or you want to simulate one beyond what you can find available today, then you can use QQuantum, the library under the hood, to run those simulations. In fact, it's so powerful that it also powers many of the most popular other frameworks. Not that we don't see ourselves in QWC as being in competition with these frameworks. We integrate with them, we work with them wherever we can, but they also draw on QQuantum in many cases to allow the simulation of quantum hardware for testing out quantum algorithms. And right down the bottom, we have DGX Quantum, which is an actual hardware reference architecture for allowing the connections of quantum hardware and conventional supercomputing hardware. And I will, I think, refer to that a little bit in a second as well. Okay, so this is to wrap up the point I've just made with all those logos and put many of them on the same page. We work with partners. We partner with more people than anyone else. These are people who we support to do their research, and that's what we care about. So if you're not on this list and you think you should be, please come and see me. And I'm sorry, I'm sure this list is probably missing people that I should have added on since the last time, and I apologise for that. But this is where we sit. We sit as a node in the ecosystem, and we want to help everyone. It's one of the reasons I love working at NVIDIA. As I mentioned, I'm very passionate about quantum computing. This is a place at which I get to work with everyone and see everything that's happening, and there could be nothing better than that. Okay, how much time do I have left? Minus what? 3 minutes. 3 minutes, okay, perfect, thank you. So I'm going to talk very quickly to each of those challenges I mentioned that I think stand between us and large-scale accelerated quantum supercomputing, and how we are working on those and how our tools are being used. First one, we need to build better quantum hardware. This is perhaps a less appreciated use of simulation of quantum, right? People think of simulating a quantum computer to test an algorithm on it. If you want to build a better qubit, you need to simulate that qubit. So for as long as anyone can think of, for example, when we build GPUs, we don't just tape out a GPU, we simulate how it will behave, rather than tape it out many times and incur huge expense in making those learnings. It's very hard to do that kind of electronic design automation with quantum hardware, because simulating quantum hardware is difficult, especially when you want to simulate the noisiness of it, which of course you do if you're trying to make the qubits less noisy. And so we have lots of partnerships in which we are using tools inside QQuantum, our simulation engine, to simulate realistic noisy qubits and help partners develop their qubits better. And in fact, we have an integration with QTIP, which recently we've announced, and which AWS and Sherbrooke have been using to do that kind of hardware research. We've had projects in the past with Google doing this. And so it's a really interesting aspect of simulation beyond just developing better algorithms. But of course, you do need to develop better algorithms. This is perhaps one of the most important areas of research in quantum as well. And we have got a number of projects on this that I'll quickly touch on. We have a project we've talked about, and there's been announcements about today with EPB and ORNL, where where we've been working on applying or developing better algorithms using QWC for things like grid optimization that are hybrid, that use both classical and quantum resources, using IonQ hardware alongside ORNL's NVIDIA DGX systems. We've worked with HPE on circuit knitting, a problem you may have heard of, where you try and think of how you compile quantum algorithms effectively over different disparate resources. And really interestingly, we've had a project with the University of Toronto and St Jude's Children's Hospital, where we are bringing AI to the way that people develop quantum algorithms. And this is a huge area I wish I'd actually planned to touch on more, which is how AI algorithms, as well as AI supercomputing hardware, are changing how we design quantum applications. And the last thing I'll touch on is scaling quantum error correction. So we need error rates much lower than you can get in physical qubits. That's why we want to use quantum error correction. Those arrows are fantastic. So these extremely large arrows are obfuscating what I wanted to show, which is the process of quantum error correction involves looking at qubits, taking some information from those qubits, passing it to an AI supercomputer, running a very hard decoding algorithm, a classical algorithm, sending back information based on that calculation to effectively correct those errors. There's more nuance than that, as most of you in this room may know, but that's the idea. And scaling this quantum error correction is really what we need, but it needs development in hardware and software. And so we have been working with partners such as QWC to develop decoders, that decoding algorithm, not only to run it on GPU machines so it can run faster and be parallelized, but also to see how AI algorithms can do that decoding. And we've had this amazing work where we train an AI model to do the decoding. Not only is it interesting that the AI might outperform more rote standard algorithms, which is not surprising because there's a lot of out of distribution effects in things like decoding with the noise involved, but also you can train that on synthetically generated data. So you use a simulator of a quantum computer to generate lots of training data. You train the AI model, and then you fine-tune it on actual data from real quantum hardware, which massively reduces the burden of how many times you need to run your QPU to get the data, and allows you to scale this realistically. And that's what we're exploring now. So currently decoders need to be much, much quicker, and they need to work on much, much bigger quantum error correcting codes. And to be in that regime that you really want to be in, so lower time taken to run and running on higher codes, you really need to get from where we are today with current decoders. And there's different ways you could do that, one of which is possibly using AI to make current decoders or replace current decoders with much, much better algorithms. And we have a library. I told you about these QWC libraries that sit on top of all our other platforms. We have one of those called QWC, and that basically packages up functionality for QEC researchers like decoders and like quantum error correction codes, so they can use them out the box to model the systems they want to run. And I won't go through this thing on the right-hand side, but essentially we have made that so it integrates with the ways people work with things like Google STIM and can produce detector error models so that you can very easily run quantum error correction circuit on realistic noise models of hardware, and then also actually run a decoder straight out the box in that system and see how it performs. Okay, that's me. I'm obviously going to plug, if you're still in GC, if you're still in DC on October 27th, we have GTC DC. There'll be an awful lot of quantum there. So hopefully I'll see you there, and we'll also be announcing some more exciting results in these areas I've talked about. I'm sorry if I went over time slightly, but thank you for your attention.